Hello students, I am Professor Dheeraj Kumar Singh from Department of Mechanical Engineering, Sagar Group of Institutions, Sistekar, Bhopal. Dear students, today we are going to discuss some numericals on first law of thermodynamics, that is steady flow energy equations. Question number 1 is, consider steady flow of air and specific heat at constant pressure is given 1.005 kilojoule per kilogram in an adiabatic passage. That means heat transfer from the passage is 0, that is our passage is insulated. Now air enters the passage at 100 kPa and 500 Kelvin, that means pressure is 100 kilopascal, temperature is 500 Kelvin and at a velocity of 150 meter per second. Velocity is also given 150 meter per second at inlet, and air exits the passage at 510 Kelvin. That means temperature at exit is 510 Kelvin. Assume air to be an ideal gas and neglect gravitational effects. Right? So prove that it is a case of diffuser. Okay, so already it is given in the question that it is a case of diffuser. We just have to prove it. So how we will prove it that it is a case of diffuser? So dear students, we know nozzle is a device which increases the velocity or kinetic energy of a fluid at the expense of pressure drop, whereas a diffuser increases the pressure of a fluid at the expense of its kinetic energy. That means in diffuser, kinetic energy will be less at exit. So here at inlet we are seeing that kinetic energy or the velocity is 150 meter per second. If our velocity at exit will be less than 150 meter per second, then we can prove it easily that it is a case of diffuser. So in any numerical problem, first we will write the given things, the given values. So at inlet we know the pressure P1 equal to 100 kilopascal, temperature T1 500 Kelvin and velocity C1 150 meter per second. And at exit temperature T2 is 510 Kelvin and we have to find out velocity at exit. If we will find out the velocity at exit and if our exit velocity will be less than the inlet velocity, then we can prove it easily that it is a case of diffuser. So dear friends, it is an open system. So in open system we can apply steady flow energy equation. So by applying a steady flow energy equation at inlet and exit, we can write the equations like this: H1 plus C1 square by 2 plus GZ1 plus Q equal to H2 plus C2 square by 2 plus GZ2 plus WCV. H1 is specific enthalpy, C1 is our inlet velocity, GZ1 is our potential energy and Q is our net rate of heat transfer. Similarly in the right hand side, W is our net work transfer, net rate of work transfer. So for nozzle and diffuser we have discussed, and we know potential energy changes can be neglected, and here we can see in question that it is an adiabatic passage, so heat transfer is also 0 and WCV are also neglected because there is not work done on the system or work done by the system, so we can neglect WCV as well. So what we have left now, the equation will become H1 plus C1 square by 2 plus H2 plus C2 square by 2. Dear students, there is one very important point which we have to understand. What? That our specific enthalpy unit is kilojoule per kilogram, right? But we can see here our velocity. The unit of velocity is in joule per kilogram. It is not in kilojoule. So for converting it in kilojoule, we can see here, for converting it in kilojoule, we can see here that H1 is replaced by CPT1. We can see CPT1 plus C1 square by 2 into 1000 we have done. Why we have multiplied the denominator by 1000? Because we want our kinetic energy expression should also be in kilojoule per kilogram. So we have multiplied the numerator by 1000 and denominator by 1000, right? when we have multiplied the numerator and denominator by 1000, the numerator will become kilojoule, right? And we have to multiply the denominator by 1000, right? So that's why we have written here Cp T1 plus C1 square by 2000 equal to Cp D2 plus C2 square by 2000. Now after putting the values, we know that Cp, the value of Cp is already given in the question, that is 1.005 kilojoule per kilogram Kelvin. So we can put the value of Cp 1.005 into temperature T1 at inlet is 500 Kelvin plus velocity at inlet is 150 meter per second. So 150 square divided by 2000 equal to 1.005 into 510 is the temperature at exit plus C2 square by 2000, and we have to find it out the exit velocity C2, right? So after solving the equation, we are finding C2 equal to 48.9 meter per second. So dear students, we can understand it very easily that our inlet velocity is 150 meter per second and our exit velocity is 48.9 meter per second. That means our C1 is greater than C2 and C2 is less than C1. So exit velocity, if the exit velocity is less than inlet velocity, then yes, we can say it that it is a case of diffuser. Here also I have written, as we can see here, the C1 is greater than C2, that means velocity is decreasing at exit, so it is a case of diffuser. So we have proved it very easily that this is a case of diffuser. Now move to the next question. Next question is, air enters an adiabatic nozzle at 400 kilopascal and 900 Kelvin with negligible velocity. Means in question we are having a nozzle which is well insulated, right? Adiabatic nozzle which is well insulated, that means Q equal to 0, and at inlet pressure is given 400 kilopascals, temperature is also given 900 Kelvin, and velocity is 0 meter per second. Now if the flow is ideal and exit pressure is 100 kilopascal, in question it is also saying that flow is ideal, right? And exit pressure is 100 kilopascals. Here it is given 100 kilopascal. So find out exit temperature in Kelvin and exit velocity in meter per second respectively. So we have to find it out, exit temperature of the nozzle and final velocity, exit velocity of the nozzle. And for air, adiabatic index is given, gamma equal to 1.4, and we have already seen it that it is a case of ideal flow, right? So we can apply ideal gas equation here. So first of all, in any numerical problem we can write given things. So at inlet we can see the pressure P1 is equal to 400 kilopascal, temperature T1 is equal to 900 Kelvin, and velocity C1 is equal to 0. And at exit we can see pressure P2 equal to 100 kilopascal, temperature T2 equal to, we have to find it out, and velocity at exit also we have to find it out. So dear students, first of all we will try to find out temperature T2 at exit. So how we will find out? By the help of ideal gas equation we can write this formula, T2 by T1 equal to P2 by P1 to power gamma minus 1 divided by gamma. We have already seen this equation, this formula in our last classes. By the help of adiabatic equation Pb to power gamma equal to constant, we will be able to find it out. So from here, from this equation we can find out T2 very easily because we know T1. So T2 equal to T1 into P2 by P1 to power gamma minus 1 by gamma. So the value of T1 is 900 Kelvin, pressure P2 is 100, and P1 is 400, and the value of gamma is 1.4. So by solving this equation we are getting exit temperature as 605.7 Kelvin. So 605.7 Kelvin is our exit temperature. So in the case of nozzle, by the help of ideal gas equation, if that condition is given in the question, so we can find it out very easily, our exit temperature. Now for finding out exit velocity we have to apply steady flow energy equation at 1 and 2. So now we apply steady flow energy equation at inlet and exit at 1 1 and 2 2. So here by applying steady flow energy equation, we all know, dear students, H1 plus C1 square by 2 plus GZ1 plus Q equal to H2 plus C2 square by 2 plus GZ2 plus WCV, and we know the assumptions that WCV will be 0, potential energy changes we can neglect in both sides, and as the nozzle is adiabatic, heat transfer, net rate of heat transfer is also 0, and in question inlet velocity is also given 0, so we can replace our kinetic energy at inlet as 0. So what will be remaining? H1 equal to H2 plus C2 square by 2, and we have to find out our exit velocity C2 here. So at the place of H1 we can write CPT1, and at the place of H2 we can write CPT2 plus C2 square by 2000. By putting the values easily, we know for ideal gas and for air, specific heat at constant pressure is 1.005 kilojoule per kilogram Kelvin. So here we can write at the place of Cp 1.005, and at the place of temperature T1 we can write 900, right? And here in the right hand side we can write at the place of Cp 1.005 into at the place of temperature T2 605.7, which we have found out here. So we can write it plus C2 square by 2000. So by solving this equation we can get C2 square equal to 591453, and after solving it we can get the exit velocity as 769.11 meter per second. So dear students, in this question we have found out our exit velocity, right? C2 equal to 769.11. So in these questions we have to look out at the given sentences very carefully. If here if it would not had been written that flow is ideal, so we will not be able to apply that equation. So here it is written that flow is ideal, then only we have applied this equation T2 by T1 equal to P2 by P1 to power gamma minus 1 by gamma, right? So in this way we have to read the expressions or read the sentences very carefully for finding out the solution of the questions. Now move on to the next question. Our next question is, the mass flow rate of air in a compressor is 1 kilogram per second. So this is a case of compressor. So here it is written that mass flow rate of air in a compressor is 1 kilogram per second. That is, m dot is given, m by t is given 1 kilogram per second. The conditions at the inlet are 0.1 megapascal and 300 Kelvin. That means pressure at inlet is given 0.1 megapascal and temperature at inlet is given 300 Kelvin. The pressure at the exit of the compressor is 1 megapascal, and here pressure at exit is also given 1 megapascal. Assuming the compression process to be adiabatic and reversible and air to be an ideal gas. So very clearly they have called that compressor is well insulated, right? They have told, so net heat transfer will be 0, and they have told in the question that air to be an ideal gas. That means we can apply ideal gas equations in this question easily. Now find the power input to the compressor in kilowatt. Finally we have to find out power input to the compressor. So dear students, in any numerical question, first of all we will write the given things or the given inputs. So at inlet we know pressure P1 equal to 0.1 megapascal and temperature T1 equal to 300 Kelvin. At exit pressure P2 is equal to 1 megapascal and we do not know the temperature, right? So first of all we find out the temperature, and then we will be able to apply it in our steady flow energy equation, and we will be able to find out our power input. So here we can see from steady flow energy equation we already know the equation of compressor work is H2 minus H1 kilojoule per kilogram. So by applying a steady flow energy equation we can find out that expression W is equal to H2 minus H1, enthalpy at exit minus enthalpy at inlet. So the unit of this work transfer is kilojoule per kilogram. Now we have to find out the power input in kilowatt. So we will just multiply the mass flow rate into this compressor work. When we will multiply, then we can see the unit of mass flow rate is kilogram per second and unit of compressor work is kilojoule per kilogram. Kilogram get cancelled in numerator and denominator, and kilojoule per second will be remaining. So we know kilojoule per second is known as kilowatt. So for finding out power input, we will have to take the product of mass flow rate into compressor work, and we know now we can write the expression for power input as m dot h2 minus h1. As we know, h2 minus h1 is our compressor work, and again we can write it like that: P input equal to m dot, we can write for the place of h2 cpt2 and at the place of h1 cpt1, right? So this is our equation 1. So from the help of ideal gas equation, now we will be able to find the temperature T2, exit temperature, because here we know inlet pressure, inlet temperature and exit pressure. We only don't know the exit temperature. So adiabatic for air, and air is behaving as ideal gas, so we can take gamma value 1.4 for ideal gas or for air. So here we have applied the equation T2 by T1 equal to P2 by P1 to power gamma minus 1 divided by gamma, and we have found out the value of T2 here finally. So the value of T2 is 579.2 Kelvin, right? And when we have found out the exit temperature, then just by putting this value in equation number 1, we will be able to find out our power input. So putting the values of T2 in equation 1, that is P input equal to m dot cpt2 minus cpt1, and by putting the values here, we have got power input. So now we have got the value of power input as 280.59 kilowatt. So what we have done in this question, we were not aware of exit temperature, and we had to find out here power input. So first of all, we have found out the exit temperature by the help of ideal gas equation, and then by steady flow energy equation we have found out our power input to the compressor in kilowatt. Now move to the next question. This question is basically based on turbine. So now look at the question. In a gas turbine, the gas enters at a rate of 5 kilogram per second, means mass flow rate they have already given 5 kilogram per second, with a velocity of 50 meter per second and enthalpy of 900 kilojoule per kilogram. So at inlet they have given C1 velocity 50 meter per second and H1 enthalpy, that is a specific enthalpy, basically they have given 900 kilojoule per kilogram, and leaves the turbine with a velocity, means exit velocity is 150 meter per second and enthalpy of 400 kilojoule per kilogram. Exit enthalpy they have also given, that is 400 kilojoule per kilogram. Now the loss of heat from the gases to the surrounding is 25 kilojoule per kilogram. This is very important sentence we have to understand here. The loss of heat from the gases to the surrounding is 25 kilojoule per kilogram. Dear students, here heat is rejected from the system. That means in our final expression we have to take that net rate of heat transfer is minus 25 kilojoule per kilogram, because heat is getting lost by the system, right? So it is heat rejected from the system. So we will take it as negative 25 kilojoule per kilogram. Now assume the gas, for gas R is equal to characteristic gas equation they have given 0.285 kilojoule per kilogram Kelvin, and specific heat at constant pressure they have given 1.004 kilojoule per kilogram Kelvin, right? And the inlet conditions to be at 100 kPa and 27 degrees Celsius. Two more things are given here. Inlet pressure they have given 100 kilopascal and inlet temperature 27 degrees Celsius. So we can convert this 27 degrees Celsius into Kelvin by adding 273 in it. So finally determine the power output of the turbine and the diameter of the inlet pipe. So dear students, they have asked us to find out the power output and what will be the diameter of the inlet pipe, means diameter here at 1, right, and power output. So in any numerical question, as we have already discussed, we have to note down the given quantities, right, given values. So here we can see mass flow rate in the question we have seen 5 kilogram per second. So m1 dot equal to m2 dot equal to m dot. So mass flow rate is 5 kilogram per second, right. Now at inlet, velocity is 50 meter per second given, pressure 100 kilopascal at inlet, and net rate of heat transfer is minus 25 kilojoule per kilogram because heat get lost from the system, right. Enthalpy is also given at inlet 900 kilojoule per kilogram, and temperature was in degree Celsius, so we have to convert it into Kelvin. So 27 plus 273, now it will be in Kelvin, 300 Kelvin. Now at exit we can see velocity is given at exit, that is 150 meter per second, and enthalpy is also given, that is S2 equal to 400 kilojoule per kilogram. So now dear students, if we want to find out the power output of the turbine, right, so always we know that power output will be in kilowatt. So here we can see, now we apply steady flow energy equation at 1,1 and 2,2, at 1,1 and at 2,2. This is our control volume, this is our turbine, right. So from here mass is entering the turbine, and here is mass is leaving the turbine. So we have applied the equation here, steady flow energy equation, m dot into h1 plus c1 square by 2 plus gz1 plus m dot into q equal to m dot into h2 plus c2 square by 2 plus gz2 plus wcv dot. Right, it is also getting multiplied, control volume work got multiplied with mass flow rate. So when we multiply this specific enthalpy or specific quantities expression with mass flow rate, then we will get the units in kilowatt, right. So that's why we have multiplied all these specific quantities with mass flow rate, that is m dot. So by solving these expressions we can get here w dot cv equal to m dot into h1 minus h2 plus c1 square minus c2 square divided by 2000 plus m dot into q. So after putting the values we can get the answers. So dear students, we know w dot cv is equal to, that is basically w dot cv is nothing but the power output of the turbine. This is power output of the turbine, because control volume work multiplied with mass flow rate, and it is giving us power output of the turbine. So 5 is the mass flow rate, and here we can see 900 is the enthalpy at inlet and 400 is the enthalpy at outlet, plus 50 is the velocity at inlet and 150 is the velocity at outlet divided by 2000, plus we have to take our net rate of heat transfer. Net rate of heat transfer is minus 25, that is multiplied with mass flow rate 5. Okay. So after solving this equation we have got our power output as 2325 kilowatt. This is nothing but the power output we have got, and power output is 2325 kilowatt. Now students, we have to find out the diameter of the inlet pipe. So how we will be able to find out the diameter of the inlet pipe? By the help of area we will be able to find out the diameter of the inlet pipe. And what are the things we know already? So here we can see a formula, that is volumetric flow rate, that this is V1 dot is volumetric flow rate, when multiplied with area and velocity then it will give the volumetric flow rate. So here first of all we want to find this volumetric flow rate, and how we will be able to find out this volumetric flow rate, because C1 velocity is given, only this quantity is not given, volumetric flow rate. So by applying ideal gas equation PV equal to MRT we will be able to find out volumetric flow rate. So at pipe inlet we just what we have done, that we have divided V by T and here M by T. So this will become volumetric flow rate and this will become mass flow rate, and we know the value of mass flow rate. So P1 V1 dot equal to M1 dot RT1. So from here we can very easily find out volume flow rate at inlet. So V1 dot is equal to M1 dot RT1 by P1. R1 is our characteristic gas equation, is also given in question, already given in question. We know T1, we know P1. So we will be very easily finding it out here. Volumetric flow rate at 1. So V1 dot equal to m, the value of m dot is 5, the value of characteristic gas equation R is 0.285, and the value of temperature T1 is 300. So now we will take it in joule. Basically it is this value R is given in kilojoule, so we multiply it by 10 to power 3 to convert kilojoule into joule. And now our pressure is also given in kilopascal, so we will convert our pressure in pascals. So 100 into 10 to power 3, then kilopascal will get converted into pascals. After solving the equation, we can see the value of volumetric flow rate is 4.275 meter cube per second. And now by the help of this formula, volumetric flow rate is equal to area into velocity. So from this formula we can find out area at inlet, that is V1 dot by C1, and A1 is equal to volumetric flow rate is 4.275 and velocity is 50, and we can write for area, that is a circular cross section, pi by 4 d1 square, pi r square, and r is equal to d by 2. After squaring d by 2 we can get pi d1 square by 4, and the expression and the value of V1 dot divided by C1 is 0.086 meter square, and from there after solving this we can get diameter d1 is equal to 0.33 meter, and if we will convert it into centimeter then we will have to multiply it with 100. Now diameter is 33 centimeter. So the final answer, that is diameter of the pipe at inlet, is 33 centimeter. So dear students, in this question we have found out power output of the turbine and diameter of the inlet pipe with given conditions. So that's all for today's class. Thank you.